NASA's Transiting Exoplanet Survey Satellite, or TESS, hunts for planets around other stars by scoping out tiny dips in the host star's brightness. TESS also provides mountains of star data that we can search for signatures of stellar rotation, but so far the telescope's systematics, its instrumental and observational search patterns, have confounded searches for periods longer than 13.5 days. Deep learning, a form of artificial intelligence, brings a new set of tools to the table, but can we use it to learn the systematics and recover those hard-to-get rotation signatures? I'm Zach Claytor from the University of Hawaii Institute for Astronomy. In this Aloha brief, we're going to explore this question and more as we dive into my paper, Recovery of TESS Stellar Rotation Periods Using Deep Learning. The paper has three main parts. First, we model the star spot evolution and light curves with ButterPie. Second, we build, train, validate, and test the neural network to predict rotation periods. And finally, we use the neural network to recover periods from real stars. I developed ButterPie to simulate realistic star spot evolution and light curves. ButterPie is an open source Python implementation of code previously worked on by Duncan McKay, Joe Lama, Suzanne Agrane, and others. The name ButterPie comes from the butterfly-shaped pattern of spot emergence latitude with time observed on the sun, and it's written in Python. ButterPie takes input of equatorial rotation period, activity level, differential rotation shear, spot lifetime, and a few other parameters. Based on these inputs, it then simulates the emergence, evolution, and decay of active regions and star spots. From this evolution, ButterPie computes a photometric light curve. We generate 1 million light curves and convolve them with real TESS galaxy light curves. Then we perform sector-to-sector stitching. Any changes in a galaxy's brightness should be due to the instrument alone, so galaxy light curves act as the instrumental noise. We then put these light curves through a wavelet transform to generate 1 million 2D power spectra, which we use to train our neural network. We used a convolutional neural network to predict rotation periods from our simulated sample. Convolutional networks work well with time series and image data because they can extract high-level features from data, such as the power spectrum peaks, as well as noise-related features. We split our 1 million wavelet transforms into training, validation, and test sets. The training set is used to fit the parameters of the network, while the validation set is used to determine when to stop training. This prevents the network from overfitting the data. The test set is then used to judge final performance of the network. Our network predicts the rotation period and its uncertainty, a process called heteroscedastic regression. Here, I'm showing the overall period recovery for the 100,000 objects in our test set. The recovery isn't great, but predicting the uncertainty allows us to filter the predictions and see what the network thinks it predicts well. When we limit the sample to the half with the smallest predicted fractional uncertainty, the recovery results improve dramatically. This has two takeaways. One, we can predict rotation periods longer than 13.5 days from TESS-like data. And two, predicting the uncertainty allows the network to tell us which predictions are reliable and which ones are not. Finally, the biggest question, does this work on real data? Can we recover long rotation periods from TESS light curves? To test this, we selected 100 stars observed by the Kilodegree Extremely Little Telescope Survey, or KELT, for which periods had been previously measured. We then visually inspected the TESS light curves and kept only the 26 where rotation was clearly visible. Taking wavelet transforms and feeding this into the neural network, here's what the predictions look like. We successfully recovered rotation periods longer than 13 and even 27 days. For most of these stars, the dominant source of power in the power spectrum was TESS systematics. These represent the lowest hanging fruit, though, the highest amplitude signals. But it demonstrates that deep learning does have the power to learn TESS's patterns and predict rotation periods despite them. With deep learning, we may finally have the potential to move past the barriers that have obstructed stellar rotation studies with TESS. Moving forward, we hope to measure rotation periods near the ecliptic poles, where TESS monitors stars continuously for almost a year at a time. For more information, check out the paper posted on the archive. The code I developed to simulate spot evolution and light curves, ButterPie, is available on GitHub, and soon the neural network code will be as well. Please support me and other IFA grad students as we advertise our work by liking this video and subscribing to the UH Institute for Astronomy YouTube channel for more content. Thanks for joining, and until next time, aloha.